to class. So yesterday we introduced the concept of composite rule. It can be composite trapezoidal, composite Simpson, composite Bose rule, anything that is composite. So as explained, the purpose of the composite rule is to allow for convergence. That is, for instance, for the trapezoidal rule, we saw that it is defined only over an interval of originally, if I have an interval AB, right, I want to approximate a definite integral from A to B, right? I'll keep that length. That is, the length of the interval will remain B minus A. You see, which is very large, because if A and B are far from each other, then because you'll be multiplying by H by 2, the result will be very large, so it will not be accurate, right? Okay, now for the Simpson rule, we saw that we can divide that interval into 2. Now the purpose of the composite rule is that we allow the interval to be partitioned by, say, n subintervals. By so doing, we will apply the Simpson rule or the trapezoidal rule to each subinterval. Now, if you take n subinterval of a given interval AB and you partition it into n subinterval, you agree with me that each subinterval length will be very small. And in that case, h will be small. And then when you multiply by the expression or the evaluation of the function at the end point, it will give you something that will be accurate, more accurate compared to the original interval AB, which is really large, right, in that case. So if you can partition a smaller interval and apply the rule to each subinterval, then we are guaranteed that in the long run, as our n becomes very large, the integral will convert towards the exact value. So that's the idea behind composite rule. So let us look at what we did with the Simpson rule. Sorry, I said Simpson. I mean the trapezoidal rule. So for the composite rule, we saw that the original interval AB can be partitioned, right? And to each sub-interval of the partition, x sub k minus 1 to x sub k, you can apply the rule to this smaller sub-interval. Now, if you apply the rule to this one, you agree with me that this will be h by for the trapezoidal only, right? For other rules, we will do the same thing. So this integral for the trapezoidal I will subscript it with k to indicate that it's in a sub-interval. So that will be h by 2. Now this h will be b minus a by n. You see, instead of b minus a, the original long interval, now we have a smaller sub-interval. If you take the length to be b minus a by n, if n is large, I have a smaller sub-interval. So for this one, the trapezoidal rule applied to this sub-interval will be f sub k minus 1 plus f sub k. You see? And then we can sum. Now, if we sum this, it gives us this expression, right? Why? Because if I apply this, we can see that this will become this sum. So h by 2 does not depend on k. I can take it out of the summation. Then we have this. Right. So this is the expression h by 2 into the sum of this factor x sub k minus 1 plus f sub k, which is exactly what you have here. You see? And as I explained, because we are summing here, if this subinterval is an inner subinterval, all the inner point will be summed twice. Right? You agree with me that all the inner points will be summed twice. Let's look at another example. Let's say that this is our, okay, let me use a different slide to make it easier for us. If I use this instead, this one, right? Because here at least I can manipulate. I can manipulate the inner point as I want. All right, so this is 28. Okay, now if I take this, so this is the original interval AB. Now we assume that we are inside somewhere here. We have some inner point. So let's say these subintervals. Okay, let's say that here we have a certain x something. Is that okay? So this is x0, which is A. And this is xn, which is B. Okay, now here we have x1, x2. Okay, we are somewhere here, xk minus 1, xk, and it continues somewhere here. This is xn minus 1, and so forth. So now, I assume that in this summation, in the original summation, this one, because this is my summation here, this summation, when k is equal to 1, we are using f0 and f1, so we are here, these two, right? Obviously, if I say k equal to 1, I'm using already a point of the boundary here, x0. And if k is equal to n, I'll have f sub n minus 1 and f sub n. So fn, that is with this last point. Okay. Now you can see that the endpoints, this one and that one, that is x0 and xn, will not be evaluated twice. That is, you will not compute f sub 0 twice or f sub n twice. because there is only one subinterval that contains x0 and only one subinterval that contains xn. Now, if I use this interval, this is the first subinterval, and this is the second. You can see that the first and second subinterval have a common point, which is this one, right? So meaning that when I will integrate like this from x sub 0 to x sub 1, and from x sub 1 to x2, you see that when I will integrate these two, of course, I put the function here in front, well, to indicate that I integrate here and there, I just factor. So you see that for this first one, for this first subinterval, the approximation will be f sub 0 plus f sub 1, right? Because of x1 here. Now for the second, because of x1 here, lower limit, for this one also we have h by 2, f sub 1 plus f sub 2. So you can see that f1 will appear in the first subinterval and in the second subinterval. But f sub 0 will only appear once. Similarly, this x2 will appear in this subinterval and that subinterval, right? The subinterval that will share x1, x2, up to xn minus 1, all those subintervals, when we will sum them up, this will appear twice. So at all these inner points, the evaluation of the function at the point will appear twice because that point is shared by two subintervals, except the first and the last one. So which means that in this summation, f A and fb, that is for this first and the last, will be evaluated only once, but for all the remaining inner points, they will be evaluated twice. That is why when we integrate from A to B using the composite rule, we will have h by 2, fx0, which is A, fxn, which is B, plus h by 2, right? The sum. Now K will take the value two, right here. You take the value 2 because for 1 is not exactly 2%, because for 1 I have two terms, but I can still, okay, let's say 1 and then here I have f sub k here plus, because I cannot say k minus 1. If I say k minus 1, when k is equal to 1, k minus 1 will be 0, which is already here. So I put 1. So f like this. Now k will go from 1 to n minus 1 because the value, wait, is it n minus 1? You take n minus 1, it should be n minus 2, because if k is equal to n minus 1, I will get fn here, whereas fn is already here in B, fb is already there. So it will be minus 2, like this, right? Then I have to put these 2. But if I want to put only a single term, then this will be n minus 1. Good. Now you see that I break this and that, I get this expression, right? Okay, now, because some of these terms will be repeated twice, here, because when I will be summing, some of these terms will be repeated twice. So I can reduce this as h by 2 fa plus fb plus h by 2 times 2 into sum. Now I group the term that will be repeated. Now this will be f k. Now here we take k running from 1 to n minus 1. You see. Now you can see that because I group the term that will be repeated twice, these 2 and that 2 will cancel out. I will finally get. So I already explained this yesterday. I'm just repeating. That will give h summation k taking the value 1 to n minus 1 f sub k, which is x k, like that. It's the same thing. So this is what we have. So you can see that f of x1, which is an interior point, is here up to this one. These are all the interior points. So all the interior points will be grouped into this summation. Now the end points, that is f of x0 and f of xn, are also grouped here. So these are the boundary points. And these are the interior points. You see, it makes life easier. So when you group, please remember what I'm explaining now, because later on you still use this. When we will be talking about iterative or recursive trapezoidal rule, you still need to use this formula. So you need to remember. I'm not saying memorizing, I say remember. So we have, for the interior, for the boundary point, you sum them. There are only two. There are only two boundary points. So for the boundary point, you have a factor of h by 2. But for the interior point, when you group them and sum them up, you have only a factor of h. There's no h by 2 because those interior points will be summed twice. And they will be added twice. So that factor of 2 will cancel out with the denominator of h by 2. So that's why we can group this way. And this is easier to remember. Group boundary point with a factor of h by 2 and interior point with a factor of h. Okay, that's clear now. Good. So that is for the composite trapezoidal rule. Composite. Okay, today, as I mentioned yesterday, we are going to tackle Simpson. Yesterday was trapezoidal. Today will be Simpson. In a like manner, for the Simpson rule, for the Simpson rule, the procedure is the same. Right, the procedure is the same. We still use this Great. But remember that originally for the trapezoidal, for the Simpson rule, Simpson. So original for the Simpson rule, we took an interval like this. Oh. We took an interval from x0 to x2. So you see that there is another point there, x1 in between, right? So meaning that we take an even number of sub-intervals. Very important, right? Here, for this one, you just took x0, x2. So there are two sub-intervals. Please remember what I'm saying. It's very important. When I explain this, some people are thinking, hey, oh, my mama hangu with the bamboo chicken that I left in the pot. So forget about your bamboo chicken for now. Okay, so you see, you have two sub-intervals. This is very important. Sub-interval 2. Sub-interval. H by what? And then here you have this point plus F what? The middle point plus. How do you remember this? Oh, guys, you are not saying anything. If I ask about your bamboo chicken, you answer very, oh, you'll be. Some people will even ask, sir, repeat the question again. So we have something like this. Is that clear for everybody? You see, we use two sub-interval of 3 points. 1, 2, 3. 1, 2, 3. We have this. We have h by 3. The previous one is h by 2. Here we have h by 3, and then we have 3 terms. 1, 2, 3. Here we only have 2 terms. 1, 2, 1, 2. Aha. Ask me a question. I want to tell you something. Ask the question. If you don't ask, I will not say it. Ask me the question, otherwise I will continue. You don't want to ask? Okay, let's continue. Since you didn't ask, I will not tell you what I was saying. Okay, so we continue. Life continues. Those who eat mahangu, yes, life continue also for them. So as I was saying, for our trapezoidal rule, I mean composite Simpson rule, composite Simpson rule, we will do something similar. Okay, so we are going to take our sub-intervals, right? Break it the way I explained. We break that, but we make sure that when we apply the rule to a sub-interval, that sub-interval has two parts, right? Because if it's a single sub-interval without two parts, or for a given sub-interval, I take the midpoint there so that I have two sub-intervals. I hope it is clear now. Is it clear for everybody? Is it clear? Is it clear? Is it clear? Guys, are we together? Class rep, if your student cannot say anything, at least you should speak for them.
Yes, Doctor.
Yes. Is it clear?
Yes, sir.
Great, great. Then we can proceed. Kashopi, is it crystal clear? Is it crystal clear to you? Okay. Yes, yes.
No, just clear. No. It is clear, sir.
What did you say?
I'm saying it is clear.
All right. Like what?
Like sparkling water.
Like what?
Like water. Sparkling water.
Which water? It depends, eh? If I go somewhere there in the north, somewhere there.
Sparkling water. Yeah.
Oh, you're right. Sparkling. Oh, you're right. Sparkling water. Great. You deserve a sparkling water as a gift. All right. Now we continue. So I said we take a sub-interval. We make sure that we have 3 points there. And that is it. Now, in order to make that clear, this is what we are going to say, that our h, right? We are not going to use this h. If you remember h here, h was b minus a by n. Now, we are going to divide by 2n. Oh, when I say 2n, it means, it just means that the number of sub-intervals is an even number. Remember this, Our x0, this sub-interval, so you see that this is an even number, 1 sub-interval and then 2. So in order to define the Simpson rule, we need 2 sub-intervals. So here we say 2 sub-intervals. So this is for Simpson. Now, if we move to composite Simpson, we need 2n. Because the original, when I apply the original rule, I need 2 sub-intervals. Now, if I want to take many sub-intervals, it will be 2n or 2m. So my n, the number of sub-intervals, should be 2 times a number, right? So if you are given the Simpson rule or composite Simpson rule, and you are given an odd number of sub-intervals, it is not possible to use it. The number of sub-intervals for Simpson has to be even. I hope it is clear. I hope it is clear to you. Clear. I hope you are not sleeping. Okay, so in this case, I'm saying that H then should be B minus A divided by 2 something, right? But that's something I call it N. But this 2N is, I can call that capital N, the number of subinterval, right? So I say capital N, the number of subinterval, is an even number. Of subintervals, right? Okay, so that is it. So the number of subintervals should be 2 times something, right? And that something that we call N is the N that you will see in the formula. So if you see N in the formula, that N is not the total number of subintervals. It is half the number of subintervals. Are we together? You see, if I take that capital N, I divide by 2. The number of subintervals, if I take this number of subintervals, N, because I already indicated here that N is the number of subintervals. If I divide it by 2, it gives N, and this N sorry, I am in a class. I'll call you after. Okay. Sure. Okay, so this N is the N that you see in the summation, in the formula. It is this N. This N is not the same as the N when you write the formula H equal to B minus A by N. This N here, in this case, is the total number of subintervals. That is N for the trapezoidal rule, or any other rule except Simpson. When you come to Simpson, this N is replaced by 2N. And that 2N is what I call capital N. So when you divide that capital N by 2, you get N. And that N is what you have in the summation. Oh, can somebody keep a bamboo chicken for me? I hope it is clear. Because I can really feel that you understand that thing nicely. Kashopi, I hope you understand this thing in another dimension.
Yes, sir, I do.
That's great. Okay, so that's the N that you find in the formula, right? This N, which is different from, as I explained, when you write H equal to B minus A divided by N. That first N in the trapezoidal rule is the same as your capital N, the total number of subintervals. Whatever you divide with is the total number of subintervals. So if I divide by 2N, it means that 2N is the total number of subintervals, which is equivalent to N in the case of trapezoidal rule. So you take the total number of subintervals here, you divide by 2, it will give you this N that will appear in the summation, in the formula summation. Okay, now let us proceed with the formula. Okay, now, you see that when I write this K running from 1 to N, this N here is not longer the total number of subintervals, but it's the number of subintervals by 2. You see, by 2. Right. Are we there? Great. Now, let me apply the rule. Let me apply the rule now. Let me apply the rule. And let's see what we get. Right. Okay, now, when I take my subinterval, I can rewrite these 2 points, this one, because we have 1, 2, 3. We have a total of 3 points, right? We have a total of 3 points. The first one here, if I call this 1, 2, 3, 1, 2, 3, because they are that is 0. The other one in the middle is 1. The other one is 2. Okay. So this is x sub 0, x sub 1, x sub 2. You can see that 0 and 2 are what we call even numbers, right? Meaning that it can be written as 2 times something, right? So I have this 0 and 2. These are factors of 2, because you can write 0 as 2 times 0. And 2, you can write 2 as 2 times 1, right? And 1, you can write 1 as 2 minus 1. All right. So each of these we can write that as, so what I'm saying is that when I write my subinterval in this form, I can relabel this. So I relabel this subinterval because I need. So my subinterval x0 x0 up to x2, right, would be mapped to, or will be transformed to, x sub 2 k minus 2, right? Because it has to be, because I can say 2 like this, k minus 1, and then 2k minus 1 plus 1. So this will be minus 2. And then there will be another point there in the middle, but let me write the last one. This one, 2k. Because the one here in the middle, there will be a point here in the middle, which will be x 2k minus 1. Because if I add 1 to 2k minus 2, I have this one. And I add another 1, I get this. So that's what we have here. Whereas here, in the middle, we have x1. We have x1. So x0, x1, x2. So this is transformed into 2k minus 2. The midpoint will be 2k minus 1, and the last one will be 2k. Right. Okay, so that is what we do in this case. All right, and that is it. We are done, right? So this interval, therefore this interval, we will get our trapezoidal rule. We just substitute those. So this implies that the trapezoidal rule becomes the Simpson, the composite Simpson rule will become okay, so it will be approximated by this summation. Okay, and we have a point here in the middle. So this is approximated by this summation k running from 1 to n. And then we have h by 3. And then we have the 3 terms. These 3 terms, we reproduce these 3 terms at these 3 points. 1, 1, 2, 3. So the terms will become, so you can see how I will map f sub 0 to f sub 0 will be mapped to f sub 2k minus 2 plus 4 f 2k minus 1 plus f sub 2k. Right? Okay, now h by 3 does not depend on k, so I can take this h by 3 out of the summation. So this is equal to h by 3, and then we sum like this to n. You see. Okay, now something similar to the previous one will, if you recall what we said, that when we add up these terms, the interior point will be double and something like that. Now, let us look at what will happen here.
I say, is it not 2k?
Sorry?
Is it not
Oh,
f of 2k?
yeah, thank you. Okay. Thank you. Yeah, okay. Great. Okay, so I was saying that something will happen here. Let us look at a particular case. You see that there are terms. The first and the last one also will be isolated, right? Because the first and the last one. I hope you understand what I mean. Okay, so when I will be summing, the midpoint, the point there, this one, the midpoint, this one in the middle, will not be affected, right? This point here. Okay, let me take it for 2 inner points. You will see exactly what will happen. So if we take 2 inner points here, this is we have the first subinterval, this one. We have x0. We have x1 here, and then this is x2, right? And then the next one, this x2 will be the first point, and then we have x3 here, and then x4, right? So this is the first subinterval. The second subinterval is this one, and then the next one is this, where we have x4, x5, x6. You see that all these even numbers, or even, sorry, odd subscript 1, 3, 5 are inside. They will not be double, right? Because x1, you can see that x1 will appear only once. But this x2 will appear in 2 subintervals. It will appear in the first subinterval and in the second subinterval. You can see that x2 will appear here and it will appear there. x4 will appear here and it will also appear there. Similarly for x6, I hope you see the pattern now. Now we have x6, x7 here, x8. And similarly, so you see that the endpoint of each subinterval which have even subscript, right? For each subinterval, the endpoints have even subscript. They will be repeated except the endpoints. Okay, so if I continue the process like that, up to the last one, let's say that this is the second last. Right? Okay, so if this is the second last, so this will be, this is x to n, which is the last point here. This is 2 n minus 1, and this is minus 2. Right? And this is 2n minus 2 here, n minus 3, minus 4. You can see that this and the previous, right, which is somewhere there. Now this one and the next, they will be repeated. Now, you can see that the first and the last one appear only once. So we can group the first and the last one in the same way we group f of A, f of B. So this is f of A. Or this is A if you want. This is equal to A. And this is equal to B. So A and B will be grouped separately because they only appear once in the summation. Whereas all the other even subscript appear twice, but the odd subscript appear only once because they are at the center of each subinterval. Whereas the endpoints will appear twice. Okay, now we can regroup this. So finally, I can group this, right? From this explanation, we can group this. So from the above explanation, if we call, so if we call this F, so we will call this S, F, H, which is Simpson. This stands for Simpson, right? Okay, given by this. Now, if we group the terms, I already indicated that we can group the first one, F0 or F of A and F of B, the first and the last, right? We can group the first and the last. So this will give us H by 3 FA plus FB, right? Okay, now, this is the first and the last. Now we can group the odd subscript and the even subscript. We saw that for the odd subscript, they are in the middle, right? So, and the middle term is this one, so we can group this as the factor of the middle term here is 4. So here we have 4h by 3, right, into the summation f sub what? 2k minus 1. So this is for the odd, right? These are odd. So I can put k here running from 1 to n, right? You can see that when k is equal to n, you have 2n minus 1, which is the middle point here, this one. So everything's there. When k is equal to 1, 2 minus 1 is 1, which is this first point here, the first midpoint here, xn, x1. So you see the formula is correct. Now plus, now the term we even subscript, we say that they will be double. Now all those points will be double, right? They will be double, meaning that h by 3 will become 2h by 3. So here we have 2h by 3 with the sum here, right? Now we will sum k from 1 to what? From 1 to what? N minus 1, because I cannot put n here because 2n is already here in B. So this will be n minus 1. Okay, let me write and check. And then this will be f 2k. Right. Okay, so when k is equal to 1, we have f of 2. F of 2 is this one, this x2. Okay, now the last one, when k is equal to n minus 1, it should be 2n minus 1 minus 2, which is this one, 2n minus 2, right? Because if I put n minus 1 there, it is 2n minus 2, which is this last point, x sub 2n minus 2. So everything is there. The formula is complete. So that's how the formulas are grouped, right? So you can group it this way. And in the note, I think it's still rewritten in this form. It is rewritten in this form. H by 3, of course, you have this one, right? Plus 4h by 3. Then you have the sum here from 1 to n. Now this is f sub x sub 2k minus 1 plus 2h by 3, and then the summation k from 1 to n minus 1. You have to remove that. F of x sub 2k. So this is the formula for your Simpson's rule, right? Okay, in the slide on the note, this one comes before this, but it doesn't matter. The formula is still the same. Okay, so I hope you understand now how those formulas were derived. I explained step by step for your understanding so that you will remember the formula. Step by step. Step by step, this is the formula. So for, or if you want, you can just write summation here. You say summation and you just say k odd, and the other one you say k even. You can still say that. But anyway. Okay, so I think we'll stop here. Tomorrow we'll look at a particular example of application. Is there any question before you stop? Yes?
Sir, can you quickly show your note, the slide that you presented before this one?
Can you repeat? I can't hear you properly.
Say, may you please share the note, like the slide of the notes of the page 36, composite Simpson rule.
You mean
Just
this,
want to check something.
this slide? You mean this slide on the screen?
Not that one on the screen, the other one.
Oh, okay. You want me to display it?
Yes. That is the correct word. Display.
Yes, this is the slide.
Okay, it's still not showing on. Okay. Oh, all right. It's fine.
Yeah, you can see that
I want
for,
to confirm
for odd
that
subscript,
that part
you sum
of
from
n
1 to
minus
n
1.
minus 1. And you have a
Yeah.
factor of 2 here. Whereas for even subscript. And now for odd subscript, that is 2k minus 1. The factor is k 4h by 3, and you sum from 1 to n. From
N,
1 to
not
n. It's not n minus 1. Please change it. Even here, of course, I change it here. I don't know if it is changed on your slide. Even the total number of points, k runs from 0 to 2n, not to n. From 0 to 2n for all the points, xk. K runs from 0, 1, 2, up to 2n. So you can see it here on the slide. Everything is changed, right? Okay. If there's no further question, I think we'll stop here. Tomorrow we will look at some example of application, and we'll do also the error analysis. Okay. Thank you for your kind attention. God bless you and see you tomorrow. Bye-bye.
Bye.